Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be starting with the TRIE playlist. The TRIE is considered as one of the toughest data structures that is generally asked in an interview. But trust me, after you watch this entire playlist of TRIE, you will be like super duper confident about any question that is asked related to TRIE. Now we will be solving the first question today in order to understand what is TRIE, when it is used. So basically, TRIE data structure is used whenever you have something like they're saying, hey, insert word, that means store this particular word. Then they're asking you, does search word, does this word exist with you or not? Then starts with word, is there any word whose prefix is this particular word? So these are the functionalities that TRIE generally helps us to implement, and we're going to learn about that in today's lecture. So let's take a quick example. So over here you see there is hello. They're saying one hello means, can you please insert hello? That means store that hello into your set of words. Next is help. Can you please store help into your set of words? Next they're saying to help. To means, does there exist any word as help? You'll be like, yes, there does exist because we already inserted one help. The next one is, does there exist any word which starts with HEL? Starts with, very important. 3 means starts with. Is there a prefix HEL among all the words? This has a hell as prefix. HEL is again a prefix over here. So there is a minimum of one word. So true again. To HEL. Does there exist a word with HEL? No, because there are two words as hello and HELP. So there does not exist a word with HEL. So you return a false. So this is what we have to implement. And for this, we are going to use the data structure which is known as TRIE data structure. Now, what is a TRIE data structure? In order to understand this, let's take some example. Assume I am asking you to first insert. Let's first understand the insert functionality in TRIE, and then we will understand the rest too, which is starts and prefix functionality. So for insert function, we have to understand what is a TRIE data structure. So in order to understand insert, what we will do is we will take some words. Let's assume I take apple as one of the words, then I take apps as one of the words, then I take something like APXL, then I take BAC, then I take BAT. So these are the 5 words that we will take in order to understand the insert functionality of the TRIE data structure. Now, what is a TRIE data structure? Let's first understand the structure of TRIE data structure. Generically, the TRIE data structure is a class or a struct if you're using C++. In C++, you can also use a class. So TRIE data structure is a struct or a class, and they have 2 member functions or 2 variables to say. Now, assuming that all the characters are lowercase, what I will do is I will say int. You can take this as anything, and the array of size 26, and there will be a boolean flag which will be false. So this is how the TRIE looks like it's a class, struct, whatever you can call it. It has a array of size 26 and it has a boolean flag. Okay, now there will always be a root. Now this is what is called as the root of the TRIE data structure. Now initially the root will be having, like, this is a TRIE. Now whenever I say TRIE, I mean that it has an array of size 26 and it has a boolean flag. Okay, so this is a TRIE. That means it has the array of size 26 and it has a flag. So I can say, let's mark flag over here. For this, flag is false. So let's mark flag as false. Now it has an array of 26, but as of now I'm not marking it. So assume this as the 26 size. Assume this as 26 size. I'm not marking it. We'll just mark whatever is required. Now let's come across and try to insert the first word, which is apple. Now whenever we are saying insert apple, what you do is you start with the root. Yes, you start with the root and you ask the root. Now remember, whenever I say 26, 0 means A, 1 means B, 2 means C, and Z means 25. This is how I will be calling up the indexing. Remember this. This is how I'll be calling up the indexing. So whenever I say, hey, for apple, what you're starting at the root. You're starting at the root. What is the first alphabet? A. The first alphabet is A. Now you're going to ask, hey, listen, does A exist in your root? They'll be like, no, all 26 are as of now empty, because whenever you just declare, that means it is empty. All 26 are empty. So you'll be like, okay, hey, listen, can you please go to the index 0 and insert A? I'll be like, okay. Now whenever you insert A, just make sure for A you create another trie node. So A will be pointing to that trie node. Just make sure you create that. Now another trie, what does that signify? Whenever I say another trie, that means with a flag as false and again 26. Okay, now you have done with A. You're done with A. Now A is pointing to this. Okay, so for A, this is what you mean. So A is pointing to this trie. Now whenever you come to P, now in order to come to P, what you'll do is you'll come to A's reference trie. So you have come up to A's reference trie. Now what's the next one? P. Now you'll ask this guy, does P exist? I don't see, because it's a null. So what you will do is you will simply take a P, yes, and again you'll create a P's reference trie. So please create a P's reference trie. Again you can create the P's reference trie, and then P will be done. What's the next alphabet? Again P. So you're currently standing at P. So which is P's reference trie? This one. You'll come to here, and now you'll ask, does there exist a P? Because the next alphabet is P. No. So again you'll insert a P and you'll create a P's reference trie. So let's create a P's reference trie. Created. What's the next alphabet? That's L. Now where are you? You are over here. Who's the reference trie? Here. Does there exist a L? No. So what you'll do is you'll simply take L and you will insert it onto the reference trie of P. Insert it and make sure you create another reference trie for this, and that reference trie will be having again flag as false, and this will be the reference trie. So L is also done. Which one is the next? E. So when you come to E, where are you? You are at L's reference trie. That means you are over here. Does it have a E? The answer to that is no. So what you'll do is you will create a E and you'll create E's reference trie. Yes, you'll again create E's reference trie, but this time initially the flag will be false, because for E, when you create the reference trie, this is how the trie will be created. So A of 26, which is this, and then boolean flag equal to false. This is how it is created. But remember, whenever you come to E is completed, which means the word has been completely traversed. So it's completely completed. Now, since it is completely completed, what is the last reference that you're standing at? This trie is the last reference where you're standing at. So since the word is already completed, you'll be like, hey flag, can you mark yourself as true? We'll be like, okay, let me mark myself as true. So let's mark himself as true and keep it. So this true signifies that E, this trie, there is a word that ends with this particular E. Got this? Perfect. Now what we will do is, we'll come to the next one, that is apps. When I come to the next word, that is apps, for this A, we will be standing at root and we'll ask, does there exist an A? He says, yes, there exists an A. So our pointer will move to the reference trie of A. So we are now over here. Okay. Next, does there exist a P? Yes, there exists. So you'll now move to the reference trie of P. We will be standing here. Does there exist another P? Yes, there exists. So you'll move to the reference trie of P. So you'll be standing here when we are at S. Okay. Whenever we are at S, we will be standing here. Does there exist an S? No, because there is an L, but there is no S. There is no S. So what you will do is, you will say, okay, since there is no S, let's create an S and its reference trie. I'll create a reference trie for this and I'll keep the flag as false initially, because I'm creating a reference trie. So initially it will always be false. Going forward, I can say, what's the next? The next is nothing but very simple. If I'm done with S, that means the word is complete. The word has been complete. If the word is complete, you know, wherever the last reference trie is pointing, which is this, you'll just go over there and you'll say, hey, listen, can I do the flag to be true because the last reference trie is ending over here. That means this is a particular word. So that is how you insert. Okay, next, APXL. So let's again do the same thing. You'll initially stand at the root. Do you have a? You have a A. Move to the reference. Do you have a P? You have a P. Move to the reference. Do you have an X? No. In this reference, you don't have an X. Put an X. And the moment you put an X, create a reference trie. Created a reference trie. And make sure this is initially marked as flag equal to false. So A, P, X is done. Do you have an L in this reference trie? No. Put an L and again create a reference trie of this and mark flag as false. Next, does there exist any word? No. So if there does not exist any word and you have already inserted this APXL, thereby you will go back and say, okay, the last reference was standing here. So I'll just make it as true and I'll finish off my job. So if you carefully observe, for APXL, APXL, very simple. For apps, APPS, APP, and then there is an S. Correct? Because for this P, it is over here. So you can easily find this out. So it's very simple. Now for BSC, for the next one, whenever I come to BAC, how will that get inserted? On the root, do we have a B? No. Insert B. Create a reference trie and make flag equal to false. Do you have an A? No. Create an A. Create the reference trie and make flag equal to false. Do you have a C? No. Create a C. Create a reference trie and make flag equal to false. Now the moment C is over, the moment the word is over, just go back and the last reference wherever you are standing, make sure that's marked as true. That is the only thing that you have to do. Next, this is also done. BAT. For BAT, it's very simple. Does B exist? Yes, B exists. Come across here. Does A exist? Yes, A exists. So come over here. Does T exist? No. Remember, for B, this is the reference. For A, this is the reference. For T, there is no T. Create a T, and create another reference of that T. So flag equal to, initially it will be false, and once it is completed, you can go back and make it true. So this is how you can store the entire TRIE data structure. Quite simple. Remember just one thing. For A, this is the reference node. For P, this is the reference node. Remember, reference node concept is very important because A is defined by this reference node and this is the starting point. This is just the starting point. This is how the TRIE data structure is created. So that is about the insert function. Now we will be learning about the search functionality. So that was about the insert functionality. Now we will be learning something which is known as the search functionality. Now just imagine someone comes up and says, hey, can you just tell me if a word like APPS exists or not? Can you tell me if a word like APPL exists or not? How will you basically implement that? It's very simple. If you have this entire TRIE data structure created, yes, if you have this entire TRIE data structure created, the moment someone says, do you have APPS? You always stand at the root and you start. You look for the first variable A. Does there exist an A? So the reference variable is here. Yes, there exists. Does there exist a P? The reference variable is here. Does there exist another P? Yes, the reference variable is here. Does there exist another S? Yes, the reference variable is here. Right? So at the end you are standing here. Is it over? Yes, it is over. Is it true? Yes. So the last reference where you are standing, it is true, which means there does exist a word. I will repeat. APPS. You stand at the root. Does A exist? Yes, A exists. Reference variable? This one. Does P exist? Yes, P exists. Reference variable? This one. Does P exist? Yes. The reference variable, this one. Does S exist? Yes. The reference variable, this one. This is over. Over. Once it is over, the last reference where you're standing, is the flag true? Yes. Thereby, I can say this particular word does exist. So that is how you can easily search. What about APPL? Let's check that out. Does A exist? Yes. Reference variable over here. Does P exist? Yes. Reference variable, this one. Does P exist? Yes. Reference variable, this one. Does L exist? Yes. Reference variable, this one. So APPL is completed. And if APPL is completed, you're standing over here. This is the last reference node where you're standing at, because for L, this is the reference node and this is where you're standing. Is the flag marked as true? No. The flag is marked as false, which signifies there is no word that ends with APPL. There is no word that ends with APPL. As simple as that. So that is how you implement the search functionality. Now we will be doing something as starts with. That means, does there exist any word that starts with BA? There does exist two words that starts with BA. Does there exist any word that starts with APD? I don't see, because there is APP, APP, APX, but nothing as APD. Like no word starts with APD. That is what the question is all about. Let's check out if there exists any word that starts with BA. How are you going to do this? As usual, you'll be standing at the root. First letter B. Does there exist a B? Yes. Reference, this one. Does there exist a A? Yes. Reference, this one. This is over. Now at the end, if you are not standing at a null, it's very important. At the end, if you are standing at a trie, that means there was a possible prefix. Otherwise, you would not have been standing over here. If there was nothing, you never would have been standing at a trie. So if you're standing at a trie, that means there was a BA. There was a BA. Yeah, the longer word can be anything, but there is definitely a BA. That's why you started with B. For B, this was the reference. For A, this is the reference. So for B, for A, you found a reference. That's why you're standing over here. So thereby, if I'm standing at a not null position, if I'm standing at a not null position, I can say there are words that starts with BA. Let's check out for APD. A, yes. For this is the reference. P, reference. D. Does there exist a D? I don't see a D over here. Do I? No. Thereby, this will be pointing to some null. So the moment you try to access D, you will get null. So if you are encountering a null at any of these instances, and you're not encountering a trie, like A. For A, you got. For P, you got. But for D, you did not get anything. Thereby, you can say there does not exist any word that starts with A, P, D. Because for A, you got. For P, you got. For D, you did not get any reference trie. Thereby, D does not exist, which means there is no word that starts with A, P, D. So this is how a trie data structure can be easily implemented. So I hope you have understood the insert, the search, and the starts with. So remember, I will be coding the insert, the search, and starts with right from scratch. So nothing to worry about. Let us code, and the moment I will be coding this, it will get much more clear to you as I move across. So let's start coding. Code that I will be writing will be industry standard. So I'll be maintaining class, functions, and everything. There's nothing to worry. You can just follow me and you'll learn the entire stuff. So what we are given is basically a class. By the way, the C++ code is on the left, and the Java code I have pre-written because I cannot write both the codes together. So for Java people, they can just follow me when I write the C++ code, and they can just look at the transformation into Java on the right hand side. But you can follow it because the syntax is almost identical, because I'm just going to use for loop and arrays, so that doesn't matter, right? So initially, you're given the class trie, and then there's a method constructor, and then they're given insert. So there's a functionality of insert, as we discussed. Then there is something as search, when they say that, okay, take this word and tell us if it exists or not. And then there is something like boolean starts with. does there exist a word that starts with this particular prefix? Okay, so what I will do is, as I said you, that there will always be a struct node. So let's write the struct node, right? And what did I say you? There will always be a reference node. Now, my pardon, when I was discussing, I wrote int, but there will always be a node star, and you can probably keep it as links, because for every character there will be a reference link. So assuming all are lowercase, I'll keep it as link 26. Now then I'll keep boolean flag equal to false. Initially, that's what I'll keep. That is what I have initially kept. Now we have a try, right? What are the stuffs that we require? We require one stuff which tells me does there exist that stuff or not, but we'll come to that afterwards. Now assume that this is the initial stuff of struct we have. Now we are having a try. So in try, what's the first thing that we require? We definitely require the root. So I can just define the root, because initially every try will have a root. So I've declared that. And after this, what I'll do is I'll say root equal to, yes, root equal to new of node. So whenever this constructor, like whenever the class's object is created, we will create a root of new node, which basically signifies that, hey, listen, we have, this is absolutely a new object for this particular class itself. Okay, this is what we will always have. Anytime anyone creates a constructor, he'll get a new try for himself. Okay, after this we have an insert of word. So if you remember, while inserting, we always started with the root. So let's create a node star node equal to root. So this is basically a dummy variable node, which is initially pointing to the root. That is what we have started with. Now we need to insert every character. So let's just move across word dot size or length, whatever you want to take. Now, what do we want to see? Word I, because we need to check if the character, what's the character? The character is word I. Does that exist in your try or not? So for that, what I'll do is I'll just create a function bool contains key. Yes, bool contains key. I'll pass in the character. He will say me, yes, if the link, because this is what it means, links. If the links of ch minus a, because I said a is 0, b is 1, c is 2. So if this is not equal to null, then you'll be like, hey, listen, that means it does exist. That means this character does exist. So while inserting, it's very important. If currently I'm standing at this node, which is the root, if node contains key, because this node, this is the reference try that I'm standing at, and I'm calling the contains key for this, and I'm passing the character as word I. Does it contain the word I? If it does not, then what I will do is, okay, you don't contain, so you have to keep it with you. You have to keep it. So what I will do is I'll again create a function which is nothing but void put, where I say, hey, listen, this is the character ch. Yes, this is the character ch, and this is the new node that you have to put it across. So what I'm saying is, okay, that is perfect. So on links, yes, on links, that is ch minus a, can you say for this guy, the reference node is this? So basically I'm saying this is the new character, and for this is the reference node that I'm saying. So assume when you started with apple, you'll pass a and you'll pass a new try for that. So apple's a will be pointing to new try. That is what this put will do. Okay. So what I'll do is I'll say if it does not, yes, if it does not, then I'll call node and I'll say put. Can you put this apple, like word I, with a new reference node, new try? So just make sure you put this new try. So once you have put this, now apple has been put, like a has been put of apple. Now can you just go to that? So you'll say node. Can you go to the next one? So in order to get the next one, what you can do is probably we can write something as a get function, because something like node or void get, something like node star get, I will like character ch, and it will be like return, where is this pointing to? Links ch minus a. Ch minus a is where it is pointing to. So what I've done is I've put across. So I'm currently standing at the root. Remember, you're currently standing at the root. and at the root you have put across, but now you have to move to the reference try. So you say, hey, can you just move to the reference of this word? I just move to the new try. So this moves to the reference try, moves to the reference try. So this is going to happen every time. Yes, this is going to happen every time, because this is how you create the new reference node, and this is how you move. So you move to the new reference try. Now once you move to the new reference try, you will insert. Again, you will come across and you'll see in the new reference try is the word I exist. If it does not exist, again create new. Keep on going, keep on going. And once this ends, once the entire word ends, can I say this node will be standing at the last reference try? And if it's standing at the last reference try, can you say set end, something like this, where you say, can you please set the end? So probably I can also write boolean set end, where I say, okay, the flag will be turned to false. True. So basically this was the last reference node and it's a set end. So it will go to the set end and say, okay, for this node, can you just turn the flag to be true? So at the last you will turn the flag to be true, stating there is a word that exists. Now this is as simple as it gets. The complexity will be bgo of, simply bgo of length of the word is the complexity for insert, is bgo of the length of the word. Perfect. We have done the insert. Next, there is something as search. Now, when you're searching, you always start with the root node. So let's start with the root node. By the way, I forgot to scroll it through. Yeah, I'll keep it like this. So you just start with the root word, correct? And what you do is you just go across int0 to again word dot length, whatever it is, and you go across I++. Now, you're standing at node. You're standing at the starting point, that's tree. Now you will be looking for word I. Does it exist? Now how will you do that? If node contains, because you will call contains again. Remember, why am I writing these functions? So that I can reuse them. I don't have to write it again and again. This is what you call production level code. Remember, these kind of codes you should write in an interview. Then they will be like super happy. Does it contains word I? If it does not contains, in case it does not contains, then there is a problem. And if it does not contains, that means the word does not exist. So can you please return it? And if it contains, why don't you get me that? Yes, why don't you get me that? Something like node get. Just make sure you get me that. If it does not contains word I, that means it does not exist, or else you just get me that and you move across. So once you're like going to the reference, going to the reference, going to the reference. At the end, how can you determine, yes, at the end, how can you determine if this node is a word, like you have found a word? It's very simple. The last flag has to be true. So probably you can write a function as boolean is end, and you can return the flag's value. So can I say at the end, if I say at this reference is end, if that's equal to true, I can say return, or you can simply return the node is end's value. Without complicating things, you can just return this node it is end's value. Then you will easily get to know if there is a word that exists. Like you go across, and the last reference where you end, if that is end is true or not, you just simply say it. What about starts with? Like how are you going to implement it? So I'll keep the Java code as usual on the right so that you can just follow me. Now, how are you going to implement it? As usual, you're going to start off with very simple at the root. So let's start off with the root. And then you're going to go across the length, which is definitely word dot length. Okay. And right after this, what you will do is you will be like, hey, listen, does this word exist? Simple as this. If it does not exist, then it is false. If it does not exist, it is false. There is nothing to do. And if it does exist, just move to the next. Then you move to the next. And at the end, do you need to check for a true? No. If you have reached to a reference try, that means this can be a prefix. So there is no need to check for end. You can directly return a true. So the only difference between this and this is return true and return this. So if you write this code, for this search, the complexity will again be bgo of length. For this also, the complexity will be bgo of length. So that is how this will look across. So will I be running this code? Absolutely no. Why? Because I was explaining you, so it might be possible I would have done syntax errors. So for that reason, what I've done is I've pre-compiled the codes and I've submitted them at the particular platform, and I've given all the code links in the description as well as the problem link. So make sure you go to the problem link and submit the code as it is, not as it is. Like you can write your own code, but the main thing to observe is how did I code. You see, I made sure that I always have these functionalities. You will see people coding where they write these lines inside, like over here they will write it, but that's not a good practice. Generally try to create a readable code. Now you see this code is so readable. Note, okay, if it contains word, then it's false. Like if it does not contains, or else you go to the next. It's so simple, like it's so readable. If you just carefully say, it's so readable. So make sure you write the code as I have written in the interview. Then only the interview will be super impressed, and trust me, they will not get a chance to reject you. So guys, I hope you have understood the explanation as well as the code. So just in case you did, please make sure you like this video. And yes, if you haven't checked out our SD sheet, you should definitely check it out, man, because a lot of people are trying that out and they're like cracking a lot of companies. So make sure you check out the SD sheet as well. I have kept it on a website so that you get all the code links, video solutions, article links, everything. So yeah, make sure you check out all the links in the description. And yeah, if you're new to this channel, please do consider subscribing to us. And yeah, with this, I'll be wrapping up this video. Let's meet in the next one. Bye bye, take care.
Whenever your heart is broken,